So the second and fifth terms of an arithmetic series are 40 and 121. Now, we want to be very careful here because it says the second term and the fifth term. These are not sums. These are actual terms. And even though in a series we're adding things together, even though we're adding these things together in a series, they're not separated by commas, this is still, this is still the second term. And this is still the fifth term. So again, I want to approach this problem, everybody, from the standpoint of what do you need to know about an arithmetic sequence or an arithmetic series to answer pretty much any question about that series or sequence? And the answer is you need to know the first term and you need to know the common difference. This cracks the case wide open. If we know those two numbers, we can find anything. So for example, if we know those two numbers and we want to find the sum of the first 25 terms, then I could use my second sum formula, S25 equals 25 over 2, multiplied by 2 times the first term, plus 25 minus 1, times the common difference, and again, if we know these two numbers, we can just put them in here. Does that setup kind of make sense to you? Okay. So how do we find the two numbers? Well, this goes back actually to, I think, day 1. And it's going to be recurring. We're going to use the same kind of idea today, but with a little wrinkle in it. To go from this term, which is the second term, all the way to the fifth term, I need to add D 3 times. And again, I've asked this kind of question before. I'll ask it again. To how many of you could you have said I have to add 3 common differences without having to draw the blanks? Few people. Because you're going from the second to the fifth term. That's an increase of 3 places. So what we're going to do here is say to ourselves, I'll write it in green to kind of match up there, is 40 plus 3D has to equal 121. And now at least we've formalized this and we can solve this for D. I would have to take, and I'm going to ask you to help me out and check my math here, I would have to take 121 minus 40, and that would give me 3D equals 81. And then when I divide both sides by 3, I get 27. Okay, so D is 27, and I don't mean to be too demanding, but I really don't think it's demanding to expect that everybody in the room knows how to solve this equation. Just almost in a blink of an eye at this level. Subtract, I mean, I will show it, but as we get deeper into the semester, I'm less likely to show these kinds of steps. I've got 3D equals 81. Then we can divide both sides by 3 and get D equals 27. So now that we know what D is, how do we find the first term? Well, I don't need that. I don't think you need to always go to a formula. So if you know that the common difference is 27 and the second term is 40, I can just subtract 27 from 40 working backwards to figure out, I hope it's 13. Is my math right there? 13. And you know, if you were really ambitious here, and I know some of you will be like this, but I also want to caution you against checking and double checking and triple checking everything that you do, because when you're writing an exam, you just might run out of time. And I appreciate that you want to do well, right? So you check things. But if you want to really check your work here before we proceed, take 13 plus 27 should give me 40, plus 27 plus 27, plus 27. Better give me 121, and it does. Anyway, I don't think you need to do that. Now that we know the first term is 13, and the common difference is 27, we can go ahead and put 13 here and 27 here. Do you need me to finish it? Okay. If, okay, so we're done with this question, yes? Okay. Let's imagine that you're doing a similar problem and you have found the 28th term. So you were told, you know, this term, no, you were told this, let's just say this is 100, and 29, 30, 31, and the 31st term is, we'll make it easy, 109. And it was the same question. You need to find the common difference in the first term. Okay? So you would set this up the same way. You would say 100 plus 3d equals 109, and you would solve this to find d. Exact same thing we did before. If I subtract 100 from both sides, I get 3d equals 9, so d is equal to 3. I don't think anybody wants to start writing the 27 terms prior to that to get to the first term. You catch my drift here, that here it was just, well, let's just subtract 27. And the fact that I have, the fact that we subtract 27 here, and the fact that there happen to be 27 terms before this is a coincidence. Okay, it doesn't, I could have said 128 and 131. It doesn't matter. Okay. But what if you don't want to be faced with that Herculean task of subtracting? You would do the following. You would use this formula. You would put in 100 for Tn, and n is 28 and d is 3, and you could solve it that way. So I didn't mean to just suggest, well, just work backwards and find T1. You might have to use a formula to do so. Okay. Other questions? All right, so we are going to move on today, and we're going to be looking at a different type of sequence and series over the coming days. So this is lesson 1.3, part 1, which is geometric sequences. I'm going to present a problem to you first to illustrate the significance of something being geometric as opposed to arithmetic. And we got March coming up. March has 31 days in it. I'm going to give everybody in this class 100% as a final mark if you guys do something for me. And I will do it. I will make it happen. On March 1st, I want a penny from you. Not from each of you. I want the class to give me a penny. And then on March 2nd, I want you to give me 2 pennies. Now, so far, what it's looking like is I'm adding a penny as I go from one day to the next. I can see that 100% thing really grabbed your attention. I'm adding a penny, but it's not arithmetic. If this were arithmetic, then on the next day this would be a 3, but I'm going to tell you it's 4. And on the next day, it's 8. And the deal is, if you do this for all 31 days, and I'm glad to see some of you are getting your calculator out. If you do this for all 31 days, everybody will get 100% in this course. And you know what? I'll give each of you $10,000 just as a bonus. Which seems like an insane proposition, doesn't it? But let me show you what kind of money we're talking about here. Believe me, at the end of this, if you did this, I'd be very happy. I'd be happy to give everybody $10,000. So let me clear my calculator screen. 1 times 2 times 2. This is how much on the third day, correct? So every time I hit equals now, it's going to take me a day forward. This is the fourth day. It's doubling. 5th, 6th, 7th, 8th, 9th, 10th. On the 10th day, you have a debt owing to me on that day of $5.12, plus all the change before that. That's the 10th day. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. On the 20th day, you owe me, if you agree to this, 5,200. Don't forget there's a decimal here because this isn't pence, cents. $5,242.88. That's, what did I say, 20? Is that right? 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Keep something in mind here. This number right here is March 31st only. $10,737,418.24 just on the 31st day. On the 30th day, it's $5 million and change. Just on the last 4 or 5 days alone, it's probably close to 20 million. Isn't it? Just these added up. $0.671 million plus 1.342 million plus 2.684 plus 5.368. I'm not worrying too much about rounding, plus 10.737. Did I add something wrong? What did I do there? Oh, missing my decimals. Decimal. Decimal, decimal, decimal. It's a lot of money. It's almost $21 million. So it's an impossible task. Sorry to say the mark you get is going to be whatever you earn. I wish we could all be happier, but that's the way it is. The point is, this type of growth is not like arithmetic. Arithmetic on a graph looks like this. And we've seen this before. Arithmetic just is a straight line. Geometric is a curve, and it really increases rapidly. So I've already actually kind of taught you what's meaningful about a geometric series or sequence. You don't add something each time. You multiply. Okay, so let's get this lesson started. We're going to identify geometric sequences, and you do need to know the difference between a geometric and an arithmetic by words. Like, you need to know what the words mean. We're going to be determining something called common ratios. So for an arithmetic sequence, there's a common difference. A common ratio is a geometric sequence's twin to an arithmetic sequence's common difference. If it's arithmetic, there's a common difference. If it's geometric, there's a common ratio. Just as we have a formula for the general term of an arithmetic sequence, we're going to have a formula for the general term of a geometric, and we're going to be doing some problems in finding geometric terms. So to begin with, a geometric sequence is one in which, after the first term, to find the next term, you always multiply the previous term by the same number. As an illustration, consider the sequence 3, 6, 12, 24. The first term is 3, and to get the next term, you multiply 3 by 2. That would give you 6. Then you multiply by 2 again, on and on. So if I take this and multiply by 2, what do I get? 2 times 3 is 6. If I take 6 and multiply by 2, what do I get? I get the third term, 12. Take 12, multiply by 2, I get the fourth term, 24. Just in a global, general sense, does that make sense what I'm telling you? There's a common number used each time, but you're not adding it. If you were adding it, it would be arithmetic. And if you were adding it, that number would be the common difference. Common ratio is what you multiply by. So, what's my common ratio in this made-up problem? 2. I'm multiplying each previous day's value by 2 to get the next day's. In this, and it's 2 here as well, too, right? The common ratio here is 2. So, I want to really slow things down here because this can get confusing for some people. If I look at an arithmetic sequence, say 2, 8, 14, 20, this is arithmetic. Can you confirm that there's a common difference there? Common difference of 6. Okay. So listen very carefully to what we've said. We've said the common difference equals 6 because even though you add 6 to move forward, the common difference is defined by taking a term, say the fourth term, and subtracting the one before. You with me? So the common difference is something, even though it's called a difference, it's something you add to move forward. But if you want to calculate it, you take a term and subtract the term before. Well, the same kind of thing is true with a common ratio. A common ratio is the thing you multiply by to move forward, but if you want to find the common ratio, you take a term and divide by the one before it. So look at this geometric sequence that we have. 3, 6, 12, 24. You multiply by 2. You multiply by 2. You multiply by 2. But what do you get if you take the fourth term divided by the third term? 2. So the common ratio is defined as being the ratio of a term over the term before it. So if I take the second term divided by the first term, I'll get the common ratio. By the way, I don't know if I have it up here, but I will check. On the left-hand side, we're talking about arithmetic. I do. If I take the second term minus the first term, I get the difference if it's arithmetic. Here, I'm taking the second term dividing by the first term. And notice here, this works for arithmetic, even if I have on the side, and is everybody here today? I think everybody's here today. I don't know why I'm recording this. Doesn't matter. If you are watching the video, you can't see what I'm referring to, but for the common difference, I could take the 198th term minus the 197th. For a common ratio, I could take the 100th divided by the 99th. But the key difference is the stuff you're looking at on the smartboard is a common ratio calculation, whereas on the side monitor, we're looking at a common difference calculation. I'm introducing something here to try to prepare you for higher levels of math. What we mean when we say this, when you say that you take any term divided by the term before, I'll write it a little larger so you can see what I'm talking about, is you take the n plus 1th term divided by the nth term. What does that mean? It means take a term and divide by the one before it, because n is 1 less than n plus 1. So n plus 1 could be the millionth term. in which case n would be the, I regret saying a million, in which case n would be the 999,999th term. All right. Well, there's a formula here. I don't want to explain where that formula comes from. Do you remember my story about Leonard Euler as a student coming up with this formula? Okay, well, this formula that's dealing with geometric is more complicated, and it's more complicated because there's an exponent in it. And you have not been taught yet, nor will you be taught in this course, exponential math. We have whole units in Math 30 on exponents and what are called logarithms. So the mathematics of this is pretty complicated. But I want to try to demonstrate kind of where it comes from. If I go back to that sequence that I had, 3, 6, 12, 24, 48, I'm going to go one more, 96. This is the sequence that we're talking about here on this page at the top. Okay. Let me ask you a question here. What do you multiply the first term by to get to the second term? Well, you multiply by 2, don't you? This will give you the second term. How would you find the third term starting with the first term? You would multiply by 6 twice, wouldn't you? You'd multiply by 6, multiply by 6. Now, if we were adding 6 twice, you'd be adding 12. But when you multiply by 6, the behavior of numbers changes. 6 times 6 is 36. Not 6. You multiply by 2 twice, correct? Sorry. So you're multiplying by 2 and by 2. To find the next term, you'd continue that process. Are you with me? So I'll go one more. To get the fifth term, you take the first term and you multiply by 2, by 2, by 2, by 2. So my question is, how many 2's are you multiplying the first term by to get the fifth term? You're multiplying by 2 4 times, aren't you? Well, that means you're taking the first term and multiplying by 2 to the 4. Because 2 raised to the 4 means 2 times 2 times 2 times 2. And notice that this is the fifth term. So when n is 5, you have an exponent of 4. That's why the exponent on this formula, everybody, is the common ratio is raised to the n minus 1. It's kind of like our arithmetic formula, and I hate to be bouncing around here, but I think this is valuable. With the arithmetic, since arithmetic is adding, you add n minus 1 common differences. Since geometric is multiplying, you multiply by n minus 1 common ratios, which means the common ratio raised to that exponent. So in this formula, Tn is the general term, T1 is the first term, and R is the common ratio. This is fairly simple, and in fact, in many ways, it's simpler than arithmetic. It's a tidier little equation. Let's take a look at some examples here. Use the sequence shown above to create a general term and verify that it works. Okay, what does this mean? The first term is 3. The common ratio is 2. I don't know how I kept saying 6 earlier. The common ratio is 2. So the general term, and this will explain to you why this is maybe simpler. I'm going to write it this way. I'm going to put brackets around the R. And I would like you to put brackets around the R from now on. The general term is 3 times 2 to the n minus 1. You know why this is maybe simpler than arithmetic? You don't have to rearrange that. There's nothing you can do with that. You can't simplify it. That's it. That's the answer to the question, the first part of this warm-up. Now, if I put n equals 1 in here, I should get the number 3. If I put n equals 2, I should get the number 6. So let me show you, a large part of this lesson is going to be about calculator usage. That I'm going to put 3 times, I'm going to put in brackets 2, and you can argue with me and you would be correct. I don't need the brackets, but sometimes you will. Okay, and I would rather say always put the brackets around the common ratio, because sometimes if you don't, you'll get the wrong answer. And you'll see how that works in a bit. I want to raise that to, this is the little, I don't know why it's called this. It's called a carrot. Little hat, little roof. I want to raise it to the 1 minus 1. Now, I hope you would agree that I don't think we need to enter 1 minus 1. But if we did, you do need a set of brackets around the n minus 1. Because you want to raise that 2 to n minus 1. You don't want to raise it to the 1 and then subtract 1. Okay. By the way, just before we go on, I hope everybody understands that the calculator will calculate this and then multiply by 3. Right? It does the exponent first, then it will multiply by 3. It's not 3 times 2 is 6, and then you raise it to an exponent. Anyway, what do we got? Well, that's a relief, because the first term is 3. So if I now want to repeat the calculation with n equals 2, and I don't know if you guys know this, does anybody have a TI-83 calculator? If you want to go back to the same calculation, you go second enter, and then you can just go and change whatever number you want. So I'm going to put that as n equals 2, and I get 6. I would really suspect many of you understand why we got twice as much at this point in time. Because your exponent is 1 more than it was before, so you have an extra times 2. If I repeat it and I put 3 in, yeah, it works. If I really understood the nature of what's going on here, I'd go, why am I doing this? Why don't I set up my table to start at 1 and go up by 1 on automatic? And then when I look at my table, and put that expression in for y1. I had something in y1 there from the previous class. So I'm going to put in 3 multiplied by 2 raised to, in brackets, x minus 1. So rather than me repeating the calculation, I just put it in there. There's my sequence. And this is really important that you understand your table features, because it turns out, remember when we did these problems with arithmetic and I said, wow, let's just use the table? Remember that? But it turns out with some of these geometric, you have to use the table. You can't do it algebraically. You don't understand the math yet. All right, so it works. Examples, what's the general term for this sequence? So I would like everybody to write down T1 equals and write down what the first term is equal to, and figure out what r is equal to. I have the first term of negative 10, negative 10, and the common ratio is negative 2. To how many of you did you just say, well, I have to multiply negative 10 by negative 2 to get 20? Many of you, if that doesn't make sense to you, then you have to take your calculator or your head and go 20 divided by negative 10. And confirm that 20 divided by negative 10 and negative 40 divided by 20 give you the same thing. Otherwise, it's not a common ratio. So are we okay with the common ratio being negative 2? Okay. So the general term, I don't have it here, but you have a formula in the top right corner of your sheet. It says Tn equals T1 multiplied by R raised to the n minus 1. You cannot cancel the negatives here. Now, I know some of you might be tempted to go, well, negative times negative is a positive. You're not multiplying negative 10 by negative 2. You're multiplying negative 10, and there's no need to write this, but you're multiplying negative 10 by this, not by negative 2. So you can't get rid of any negatives there. Very, very basic question. Let's try another one that's pretty much identical. Write the general term. So again, in order to find the general term, you need to know the first term and the common ratio. I didn't point it out, but I hope it's obvious by looking at the previous example that if the common ratio is negative, the terms flip back and forth between positive and negative. The common ratio here is 1/2. I would prefer if we use a fraction of 1/2 here rather than a decimal. And the first term is 64. So the general term is 64 times 1/2 to the n minus 1. And that's it. Three, 9, 27. You might say, well, okay, I get the idea. But there's something unique about this. The first term is 3. The common ratio is 3. Just run that around in your head for a minute. Just roll it around and make sure you understand why the common ratio is 3 as well. This is because we go from 3 to 9 to multiply by 3, 9 to 27 multiply by 3. So we get this. But starting now and continuing until the end of Math 30-1, you're going to see more and more mathematical expressions which are disguised as apparently different looking mathematical expressions. So for example, when you get to Math 30-1, I know this doesn't really make a lot of sense to you, but I'm just going to tell you that if we have sine squared of x plus cos squared of x over tan of x, well, you know what? That's equal to cotangent of x. Now, you don't know what any of this means, but the point is, on an exam, you could be given a question where you do all this work and you get to this answer, but that answer is not one of the choices. This is one of the choices, and it's just the same thing with a different mask on. It's a different appearance, but it means the same thing. And in this particular question, one of your choices would be 3 to the n. And 3 to the n is the same as 3 times 3 to the n minus 1. How do we know that? Well, three is 3 to the 1. Yes? Okay. If I asked everybody, let's take a little detour to figure out what x squared times x cubed is, I really hope everybody would say x to the 5. Because when you multiply a common base, the base stays the same and you add the exponents. So the step that I'm not really showing here is that this is x to the 2 plus 3, which is x to the 5. We do the same thing here. We have a common base of 3, so the base stays the same, and we add the exponents. 1 plus n minus 1 is n, because 1 minus 1 is 0. Just throwing that out there because you're going to encounter these twists and turns. All right, let's try a different question. What's the 9th term of this sequence? So we're going to use the general term formula. Let me put up the general term formula over here so I can refer to it. Come on. There we go. There we go. So if I want to find the 9th term, I need to come up with the general term first. So I identify the first term in the common ratio. Are we okay with the common ratio? Multiplying by -3. Again, if you see the sign is flipping back and forth between positive and negative, you know the common ratio is negative. So my general term that comes out of that will be this, and that means that to find T9, we have to calculate that, which is what I would like everybody to calculate. I need all of you to calculate this value on your calculator. And I'd be willing to bet a large sum of money that there are 2 answers floating around out there. But I want to see them. So could you, I wouldn't be able to read your calculator without my glasses. So write down what the answer is that you get and circle it on paper. Write relatively big so I can see it. And the result, I don't know why I just didn't put some glasses on. The result is so far what I would expect, which is namely about a quarter of you are getting the wrong answer. And this is a thing that we need to make sure that we're on top of it. Oh, the odds are improving, and then they drop again. Improving, improving. No. Continuing to improve. Flipping back and forth between good and bad. Good. No. Not good. 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 I would say it's about 30% got the wrong answer. And you're sitting there, you're confident you got the right answer, right? You're looking, well, how could I possibly get this wrong? The answer is the 9th term is 19,683. Not negative. It's not negative. And I would say at least 10 of you put negative. So it's maybe a little more than 30%. So the first thing to note is let's talk about this expression here. I'm going to rewrite it 3 times -3 to the 8. Let's break this down. And this is one of these things, everybody, where seriously, it's such a minor thing from grade 8 or 9. And if you're getting the answer wrong, it's tragic because you're understanding Math 20-1, but you can't get the right answer because you're making a junior high mistake. I would like everybody to figure out, let's even make this simpler. I would like you to use your calculator to figure out what -4 raised to the 4 is. 256. If you got negative 256, you're doing it wrong. We know that this is positive 256 because it means negative 4 times negative 4 times negative 4 times negative 4. This is an even number, so you have an even number of exponents. I made a fatal teaching mistake here by choosing 4 and 4. But the bottom line is, if this were, we'll go negative 3, okay? Negative 3 times negative 3 times negative 3 times negative 3. You know that pairs of negatives become positive. Which means anytime you have an even exponent, the entire power has to be positive. So, those of you that got a negative answer for this entered 3 times negative 3 raised to the 8. That's what you did. And I'm telling you that's wrong. And the reason it's wrong is because it has to be positive because there's an even exponent. So what's your calculator thinking when you did that? When you enter 3 times negative 3 to the 8, listen very carefully to the difference between what is in brown and what is in green. What is in brown is 3 multiplied by negative 3 to the 8. It's calculating 3 to the 8, it's slapping a negative on it, and then it's multiplying by 3. What's in green, which is correct, this is what's happening. It's 3 times negative 3 raised to the 8. And we say for this, I don't know if your teachers have ever said this, you'll let me know because I'm going to ask. This is negative 3 quantity to the 8. Have you ever heard that? Never. It means the entire negative included as well. So you need to enter the negative in brackets. Now, I'm just curious. This is going to give you the answer. How many of you, knowing that now, would enter it next time and just not put the negative at all? Nobody. Okay. I wouldn't because it's even. I know it's going to be negative. But be careful because if it's odd, it's going to be positive because it's even. Okay, so we got some fundamental math here that we need to be very careful about. This is our final answer, 19,683. Let's try one more. Find T7. Well, we got some weird fractions here. Do me a favor, please. By hook or by crook, which means I don't care how you do it. I want you to figure out the common ratio. And how many of you can see what the common ratio is by looking at those fractions? Good. Just a couple people, but that's fine. What you're doing here to find the common ratio is you're using the idea that if you take a term and divide by the term before it, that'll give you the common ratio. But since these are fractions, if I want to take 5/12 divided by 5/6 on my calculator, I'd better do this. Fractions are messy if you don't have brackets around them. I get 1/2 or 0.5. I know it's 1/2 because if I multiply 5/3 by 1/2, I go 5/3 times 1/2 gives 5/6. I'm multiplying by 1/2 each time. So T7, well, let's find our general term first. Tn is T1 times 1/2 to the n minus 1. That means T7 is 5/3 times 1/2 to the 7 minus 1, which is 6. You definitely need these brackets. Please try to remember what I told you to begin with. You should put r in brackets all the time. So I would like you to calculate what this is. I'll do the same up here. That's how I would enter it. And I like this older calculator. I realize if you have an 84 or a fancier calculator, it's formatted a lot better. I get this. I've been teaching here 30 years, and for the past 10, every day that mop bucket goes by and it squeaks like that. And I have a can of WD-40 at the back. I want to go out there and that's what it is in decimal. If we go math, enter, enter, we get a fraction. And here's a very interesting thing. How many of you, when you go math, enter, enter, you don't get a fraction? And you have a better calculator. This is one of the things I like about this calculator. Some of the newer calculators, I don't know why, they can't convert it to a fraction. Weird. And I really don't understand why. Anyway, the answer is 5 over 192. Any questions with B? All right. The third term, these are geometric. The third term is 4 and the seventh term is 64. Does this problem kind of look familiar? Like, have we seen problems like this before with arithmetic? In fact, we did one earlier today, didn't we? Where we had the missing terms. I think you had asked about it. And we said, well, let's figure out how many D's we add to move forward. Well, let's do the same thing with this. First term, second term, third term is 4. Fourth term, fifth term, sixth term, seventh term is 64. Okay. Now let's forget for a second here that I am sure there are some very smart people in the room who could figure out the common ratio. Let's forget about that for a second. How can we systematically find it? Well, to go from here to here, you multiply by r, multiply by r, multiply by r, multiply by r. Does that make sense? That's what's going on. So this is the language doesn't fit the math. So we're multiplying by r 4 times. That doesn't mean we're multiplying by 4r. That's not what that means. It means we're taking 4 and multiplying by r times r times r times r. That's not 4r. It's not 4r. What it is r raised to the exponent of 4. And now this equation, we're trying to find r. You don't know how to solve this equation. Well, you probably can figure it out, but this is not a linear equation where you subtract numbers and divide by numbers to get an answer. This is really different. The first thing we're going to do is divide both sides by 4. And get r raised to the 4 equals what I believe is 16. Am I right? I think it's 16. Yeah? Okay. Now, how many of you know what r is? It's 2, right? Okay. But let me ask you a question. How many of you can explain to me what you do algebraically to get r by itself? What do we do to get rid of that exponent of 4? Because you probably know it's 2 because you're going, well, 2 times 2 times 2 times 2 is 16. You're doing it a different way. What do we do to both sides of this equation to change the r to the 4 into r? Give you a different question. If I had x squared equals 12, how do you find x? Lily? Square root. You take the square root. So x here would be equal to the square root of 12. If I had y cubed equals 40, then y would be equal to the cube root of 40. Roots undo exponents. So, how do I do this? I take the fourth root of 16. Now, how do I do that on my calculator? We will talk extensively later in this course and a lot in 30 about exponents and related topics. But mathematically, this happens on a calculator by taking the fourth root. Now, we do have a square root function. It's second squared. And if you go to math, you have a cube root function. There it is. So if I wanted, for example, what did I have? The cube root of 40? If I wanted the cube root of 40, I would do this. The question is, how do I do the fourth root? Well, I don't have a fourth root key on the Texas Instruments calculator, but when you look at math, you see option 5 is the xth root. So this is going to look like crap on my home screen, but this is how you find the fourth root of 16. You go 4, math, choose this option, 16. It doesn't look like it should. It should look like what I have written at the bottom of the screen here. It's 2. So the common ratio is 2. So what were we asked to find? T7? Nope. We were asked to find the fourth, fifth, and sixth terms. Yes? So if the common ratio is, what did we say, 2? Multiplied by 2. There's the fourth term, multiplied by 2. There's the fifth term, multiplied by 2. There's the sixth. And I do realize that many of you probably could have come up with those numbers kind of solving it as a puzzle, so to speak. But if we take a look at the final example, 3b, you couldn't do it that way. However, we're not going to do example 3b. I think you get the idea. I would rather give you 20 minutes here to work on this stuff in class than rush through another example, maybe confusing you in the result in the end. So I want to I had a couple of conversations with a couple of you yesterday. I want to remind everybody of something. When I tell you it's practice, you decide what to practice. The expectation is during class you're working on this. You're not just taking the attitude that I know how to do this, I followed along, so I'm not going to do anything. And by the way, I wouldn't take that attitude outside of class either. I would, if you're a good student, you're going to go, yeah, this made sense, but I'm going to take it home. I'm going to just make sure. Because it can snowball on you, right? You can be the best student in the world and you start putting stuff aside and it's easy to fall behind. So definitely on page 39, 1 to 5 is kind of a good set of problems. And then I've got additional problems as well. If you want to work on them, you can. So get going on this. I need to take attendance and just double check on a couple things and then I'll be around to help you out.